All right, today we're going to be talking about the states of matter. And so we're going to not only explain them and describe the differences, but we're going to look at heating curves and phase diagrams, which will most likely be new. So, first, get a few definitions out of the way, and most of these we've already covered. So, first, matter is anything that has mass and takes up space, so the tangible things that we can interact with. Energy is the ability to do work or to transfer heat, which is what we're really going to be talking about today, is the ability for matter to uh, gain and lose energy through heat. All right, it's measured by temperature. And fluid is a substance that flows, deforms, changes shape when subject to a force or stress. So don't think about fluids as you have in the past being a liquid. All right. Fluids can talk about different states, but it's a state where substances can, flow or change shape. And so, really, guys, both liquids and gases could be described as a fluid under this definition. And then a phase equilibrium, which is two or more states of matter are present at one time, which when we go to a phase diagram, we're going to kind of dive into that. So it's think about like a glass of ice water. You have both ice and water mixed together, two different phases at the same time. It's not like as soon as you mix them, that water chooses whether to be solid or liquid and jumps from one to the other. Okay? And so are four states of matter, right? Solid, liquid, gas, and plasma. And we've talked about these all before, but when we talk about solid, we have that form of matter characterized by rigidity. Everything has its spot. Now that we have our understanding of ionic bonds and covalent bonds, and we kind of understand those forces that hold them together, in ionic, we get those electrostatic forces like bricks in the wall, all right, positive, negative, that make that rigid, crystal form. And then when we get into covalent bonds, you get those intermolecular forces kind of pulling these things together. Now, with a liquid, you get a form of matter that's an incompressible fluid, right? So we talked about a fluid, again, being something that flows, deforms, changes shape when we subject it to a force or stress. Well, when we're talking about liquids, they are a fluid because they can change shape, but these are incompressible. All right. If we apply that pressure to them, they're not going to compress, or if we let off pressure, they're not going to expand. Whereas with a gas, it would also be a fluid, but it is in fact compressible. We can compress it to fit into a container of our choice. And then plasma is that electrically neutral gas of ions and electrons like the sun. All right, usually very hot temperatures. All right, and so we can see that we have this state of states of matter, and as you go from left to right, you're getting not only into the phase changes, but you're getting added energy or temperature. Okay, so if you go from one to the next, we're adding energy to the system. All right, now the real thing we want to get into is some phase changes. And so we know most of these, right? So as we move from solid to liquid, we'll have that melting, that fusion. Okay, fusion's a word we'll start to use a lot more as we get into the energy associated with melting. All right, but your fusion, then liquid to gas vaporization. Okay, and then if you go straight from beginning to end here, so from solid to gas, skip that liquid, it's sublimation. The example being snow. If we have snow on the ground, all right, not all of it melts. Some melts, but let's say you have snow and it stays at 30 degrees. The snow will still start to disappear. It won't melt. It hasn't become hot enough to melt. But for various reasons, guys, it has gained enough energy to jump from solid straight to gas. That's sublimation. Now, our opposites, okay, the opposite of sublimation is deposition, straight from gas to solid. And then gas to liquid condensation, liquid to solid freezing. All right, most of these you'll be very, very familiar with already. Okay, so then a quick thing with reaction energy, and it's really systematic energy is what we're going to talk about here, but it's energy coming into the system, energy leaving the system, okay, or leaving a substance, and we're going to call endothermic and exothermic. Endo meaning internal, exo external. So in endo, we are absorbing energy in. That would be like ice melting, right? Where you're absorbing energy and therefore it's going from a solid to a liquid. Okay? Whereas exothermic is heat leaving the system. So if you ignite something, right, you have energy that is stored within the system and it is being released out of. An exothermic process releases energy. Okay? So now we get into what are called heating curves. And this kind of explains the process of what happens as you add energy to a system. Now, we're specifically going to be talking about energy in the form of heat, okay? And so we'll talk about getting into temperature and heat. So as we add heat energy, temperature tends to go up. But it's not always that case. And this gets back to, in our definitions, what we call phase equilibriums. All right. So if we start down here at the bottom, we have low temperature, low energy. It's going to be a solid. As we add heat energy, the temperature will steadily rise until we hit our first plateau. And this will be where we have this melting taking place. And while something melts, it will stay at the same temperature. So think about that glass of ice water on a summer day, right? You have heat outside, which is being transferred into the system, an endothermic process where we're bringing in that energy, but your drink is staying cold. Well, that's because there's still ice in there. All right. And so it will stay at that temperature until enough energy has been absorbed to now melt all the ice. Now, what happens is that's when you get to the end of this plateau. So the melting takes place over the course of this plateau. And now you don't have any more solid. So as more energy is added, now we're warming that liquid. All right. Which happens with that glass. It sits there and now it's starting to get warmer. All right. Well, let's say it's a really hot day and we get up enough that now we start boiling that water, right? And so what will happen is, guys, it will again plateau. So this is with cooking, you kind of get in that. When you boil water to cook pasta, it is not an endless process. You're adding more energy. The temperature of that boiling pot does not rise further. As you're boiling it, some water will evaporate and it will stay. That liquid there, right? The liquid water will stay at that 100 degrees Celsius for as long as it takes until all of the water has been converted to gas. Now we're of course having to talk about a closed system where we would be collecting all that gas and keeping it hot, right? A little bit dissimilar to your stove. And so it'll stay there at another plateau. All right, and that is that vaporization. Okay, then once it gets to there, it'll continue to warm that gas. Okay, now obviously the exact opposite would be true if you're cooling. You could go the other way where you're cooling that gas until it begins to condense, And then it will stay at that temperature until all of it has now turned into liquid. It is condensed. Then it will continue to cool until it starts becoming a solid. And then again, the entire system will stay at that temperature until all of it is a solid. And then you'll have the cooling of the solid. Okay, and so that's your heating curve. It tells you temperatures. They will look slightly different for every different substance that you have, especially with different temperatures. Obviously, water will freeze and evaporate at a certain temperature, and an oil will freeze and evaporate at the different temperature, and oxygen will freeze and evaporate at a different temperature. All right, so from here we can also get into, and the last thing we're going to talk about is phase diagrams. Now, these ones, instead of specifically talking about temperature versus energy, we're really talking about temperature and pressure, which it seems a little bit odd, but you guys really know this, right? That you can change the state of matter, all right, solid, liquid, gas, not just by temperature, but also by pressure. So you could boil water at 10 degrees Celsius, right? You could boil water at room temperature. You could boil water below room temperature if you lower the pressure. Okay, the same way for some things that are a gas, right? Like a propane or a carbon dioxide. If you raise the pressure, it'll turn into a liquid. That's why when you go fill a propane tank, it is in fact liquid inside that because you're adding that pressure. And so what we see here is pressure versus temperature. And there's a region that is solid. If it's at any of these pressures and any of these temperatures, right, that'll be in the solid region. Now, once you're at like a pressure up here and you add the temperature, right, you start rising that temperature, adding energy, at some point it'll cross into a liquid. But depending on the pressure, it'll be a different temperature. All right, which is why water boils different depending on your elevation. Water boils at a lower temperature in Denver than it does in New Jersey. All right, if you're flying on a plane, it's even lower than that. All right, but that is that barrier there would be melting, freezing. As you go across it, going from solid to liquid, it's melting. Liquid to solid, it's freezing. Okay, and so when we get to the same here, where you go from solid to gas, sublimation deposition, or liquid to gas, vaporization, condensation, and there's this thing called a triple point. Now, a triple point is the point where everything comes together. Solids, liquids, and gases, all three can exist in equilibrium. All right, so the same way that you have that, oh, well, I have a glass of water with ice, all right, and they're existing together. Well, this would be all three can exist together: gas, solid, liquid. All right, it's called the triple point. It's a different point for every substance. Okay, but now once you get so high pressure, all right, so high temperature, you get to what's called a critical point. And at the critical point, you you can't become a liquid at any temperature or at any pressure, no matter how much you increase the pressure. You cannot become a liquid at that temperature. So if this temperature were 1,000 degrees, right? Once you hit that 1,000 degrees, no matter what you make the pressure, you can never force it back into a liquid. Okay? And so at this point, we become what's called a supercritical fluid, which we can talk about a little bit more later, but these liquids and gases are kind of indistinguishable. They're somewhat one and the same because you're following the properties and movements of a gas, but you're so condensed by pressure that you're close enough to act like a liquid. And so once you get too high, you get into what's called supercritical fluid, and uh, you can't make it a liquid anymore. It's an indistinguishable area. All right, and so that's the phase diagram, guys. Uh, we're not going to look at you knowing specifics of temperatures or pressures or this and that, but we're going to look at, what the triple point is, what the critical point is. You understand as you cross these barriers, you know, what phase changes are occurring. All right. And so that is the phase diagram and our states of matter.